Hello.
Hello.
How are you? Everybody awake?
No.
Me neither. So, later on today at 3 p.m., we have the Fail of Things in the IoT room. We have the Raise Me Resume Workshop in the Hardware Hacking Village. At 4 o'clock, all the contests end. So, Tamper Evident, King of the Hill, Capture the Flag, as well as the pinball contest you may not be aware of, happening in the Chill Out room. The score to beat is 584 million, which sounds like a lot, but it's not. Don't worry. So go beat that, win the prize. If you want to buy a fabulous LayerOne 2018 t-shirt, they're available at registration for $20. If you like this talk or missed a talk before or going to miss a talk later, you can buy the thumb drives, which have all the talks from Todd in the back after we wrap up here for $40. And at 5 o'clock in this room, we're doing closing ceremonies. After that, we kick all of you out of the rooms, and we head over to the 23B shop in Fullerton. It's a local hackerspace, which promises lots of fun, fire, hammer Jenga, maybe a Tesla coil. We'll see how it goes. Let me double check. Okay, so up next, we have a very dear friend of LayerOne, Katie Knowles, with Signal Safari investigating RF controls with RTL SDR.
The goldfish are important. Hey, so thank you all for joining me right after lunch. I know the food coma is going to kick in about, what, like 10 minutes? Right now, you think you're ready for it. You're like rearing to go. You're ready to learn. And then I'm going to see you all drooping down. So it's my job and my challenge today to keep you all awake. But speaking of being awake, who was here this morning for the, it was the wireless pen testing talk? Who was brave enough to get out of bed for that? Awesome. So you might notice, well, other question, who had the self-preservation to just stay in bed this morning? Also an excellent choice, both really good options. So you might notice there's a little bit of content overlap between this one and that one. For anyone who missed it, there was a great talk on some devices that you can use for wireless communications in, whatever you're doing on the security front. And this is a little bit more about almost the opposite. Instead of using devices, we're listening to devices. We're trying to figure out what they're like and what they're doing and what they're up to. There's a lot of mystery in the world around us and a ton of signals out there you might not have thought of. So we're going to go basically from nothing to surprise. You'll find out. So this is me making sure that my remote works. Pardon. Perfect. All right, so a little bit about what we'll be doing today. We're going to go through how RF works, how signals work, how you're going to expect devices to communicate on a basic level, and then we're going to go on an adventure, a little safari through a bunch of devices that I found in, amazing technologically advanced world of my apartment. So there's just a bunch of stuff that I use around my house. Maybe I'm lazy, I don't like turning on lights or fans or anything. I'm the ideal user for this, right? I've got a bunch of things, and they might not be that secure, but we'll learn how they work. We'll see what they do, and we'll take the opportunity to use different tools whenever we can, because that's what it's all about, right? We got to push ourselves to use new stuff and learn new things, which is really what it's all about. Once we get through that, we'll close with some thoughts on signal security and how we can continue the adventure if this has hooked anyone. There's a ton of signals out there. Some of them are really simple, some of them are really complicated, and today we're here to see if we can catch them all. Bad Pokemon jokes, I hope you're ready. So if you're curious about RF, if you're looking for good projects, I think that was the slide before this, but that's all right, it all melds together. And if you're seeking adventure, then here we go. It's the short story there. So to start things off, I'm going to go through some introductory stuff. I'll try to clip through this pretty quick while you're still awake before the food hits. This is like the, all right, go, 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 and then we'll go on an adventure, and because your brain will be moving, you'll be awake. So to start things off, RF travels as electromagnetic waves. It's kind of like light, and there's a bunch of different, RF waves. That some of them, you've got the higher frequency with the shorter wavelength, and the lower frequency with a longer wavelength. And an easy way of thinking about the relationship between the two is that an electromagnetic wave will always be going the same speed. They all go as fast as each other. They're the speed of light. So if you multiply the frequency and the wavelength, you'll get back to that speed of light. So the signals that we've got that are higher frequency, we can send a little more data because more of those wavelengths are going to pass by in a given amount of time because it's going like a little bit faster, but metaphorically faster, not literally. There's just more waves passing. Whereas with the lower frequency, we're only going to get so many, and we can only send so much data with a given wavelength. And this is it. This is how your phones work. This is how the Wi-Fi works. This is how radios work. Tons of things. So today, we're going to be looking at a bunch of those signals using an RTL SDR. So has anybody used one of these before? Cool. Has anybody really wanted to use one of these before? Like, they've been super curious. That's great. I think we've got like most of the room at this point. You're like, well, maybe, yeah. Well, hopefully by the end of this, we'll change that. So RTL SDRs are super cheap. They're a little USB device that you can plug into a computer, and they have all the circuitry that your computer needs to receive radio signals. And all of the processing of that signal can be done by software. So programs on your computer can handle it. So instead of having a giant clunky radio or, like the image of a radio operator in the middle of the century with this giant wall of things, we can just have this little USB device. This one just receives signals. So if you start using devices that transmit signals, you want to be aware of FCC regulations and the legalities of that. But for today, we're just listening and learning and finding out what's around us. So we can speculate on security things, but we don't have to worry about the transmission side. And obviously, when you add up cheap devices that do cool things with free software on Linux, you get magic. Really no way around it. That's what happens. All the tools we're doing today are using today are Linux-based. If you like Windows-flavored things, there's tools for that as well. But today, it's all Linux. So we're taking our first steps at this point. I've gotten through the intro where I'm like, this is what a Pokemon looks like. And now we're in the starting town, right? And we're ready to wander out. We kind of know what we're looking for a little bit. Maybe we think we're ready. And we're going to use a program called GQRX. So this program is one that lets you tune around for signals very easily. If you've got an RTL SDR, you can pick up like FM radio stations. Maybe there'll be some really interesting frequencies that people are talking on for a company, or police radios, things like that. You can just sort of see what's around you. And there'll be a little bit of like a demo video coming up with this. It's also got a waterfall view. So the waterfall you'll notice coming up is the view of different amplitudes over time and I'll just let you see it. It's pretty cool. It looks like a waterfall, which is why it's called the waterfall. The frequency range you can look at will be limited based on the hardware of the software-defined radio you're using. So if you've got a more advanced one, you can look at more signals. If you've got a less advanced one, you can look at less signals. So this is a video of me using it. I'm just going to turn it on with the RTL SDR plugged into my computer. And you can see right now we're at 89.9 megahertz, so we're at an FM station. And this is that waterfall I was talking about. Hopefully you can get a sense of why it looks a little bit like a waterfall now. We see the changes at different frequencies. We can see over time how it's changing and modifying. We can tune around with it really easily. We can change how we're filtering the noise out. Sometimes there'll be RF noise, so you can't hear a signal great. You want to sort of focus in on one thing so you can hear it. And we can actually type in new frequencies to look at as well. So here we can tune to a different station. Maybe I didn't like that music. Pull the scanner around. So it's really just easy to play with, fun to look at what's around and see what you'd expect from a typical radio. And then if you want to, you can look at AM, so some more amplitude modulated stuff as well, which is how a lot of the local signals that you'll find for people talking back and forth with each other will be. So here we're going to look at, I think it's like somewhere around the 400s, and there's some local chit chat going on. If there was sound for this, you'd be able to hear, maybe someone's giving a status update or asking for help or something like that for some police-related operations, which when they are unencrypted, you can tune around and listen to those, which is how, if you've ever seen those police repeaters online or something like that. So now we've played around with the signals a little bit. We've kind of had our first encounter, right? We've been like, oh wow, a signal, we found it. But now we want to see more signals, right? This is kind of like I showed you what you already know, the FM part of things with a slightly different view. But now we want to start thinking about like, okay, so the security side of things, right? How do things operate? How do things turn on and off? How can we find the application of this to something we'd be a little bit more curious about? And to get there, we're going to look at sort of the zones and the habitats that our signals live in. So we've got, tall grass and icy terrains and things like that. Here we just have different frequencies. So down towards the lower side of the RF spectrum, you're going to find AM radio. Any amateur radio operators in the room? Awesome. So I believe 10 meters to about like 80 is all in that band that I've got highlighted here. It's not all the amateur radio frequencies, but it's a lot of the ones that get used for communication back and forth. For those of you who aren't familiar with amateur radio, you can make some amazing long distance communications that way. And then moving upwards, we've got a bunch of different areas where you'll find television signals, if anyone still uses broadcast television instead of cable, FM radio, and these white boxes I've got outlined are where the control signals we'll be looking at today live. So this is the specific terrain that they live in. This is where they end up. Zooming in on those systems, we've got a few different bands. So if you're looking at control signals for close range stuff, so turning things on and off, and maybe you've got some industrial systems, things like that, then they'll probably be in these bands. So when I say the center frequency on the left here, that's how you'll hear people sort of colloquially refer to that band. So you could have something that operates at maybe like 433.9 megahertz. It would still be called a 433 megahertz device in that range. The ISM is for industrial, scientific, and medical. So these parts of the spectrum were originally set aside for industrial, scientific, and medical equipment. And then as time went on, they were sort of open to other things operating there as long as they don't interfere. So there can be some pretty serious things that need to keep operating there, and as long as your signals don't interfere with that, then they're allowed to play too. They just need to, be quiet, calm down if something more important is happening. And then the unlicensed band down here is you can just create a device that operates within the power limits of that band, so it's not too strong, works out well, and without having to register that device, it operates as an unlicensed device. So when I say licensed versus unlicensed, if you've ever gone to a restaurant and seen those buzzers or taken your phone out of your pocket or used a laptop, you notice that FCC ID, that's the license. So people have to submit information on what the device does, why it operates in those frequencies, why it needs to operate in those frequencies in order to get approval. All right, closing out on the introductory stuff here. So we've got the how do these devices talk, right? So we know where they live, we know what they look like, but what are they saying? How do we get to those ones and zeros that we're used to seeing for devices that talk to each other in a digital way? And there's a couple of pretty common ways. There's a bunch of different ones. If you start looking into this, there's a ton of different ways that are really cool that these systems communicate. But at the very basic level, we'll just talk about amplitude and frequency shift keying. So for the amplitude shift keying, or ASK, we've got some length of pulse. So the amplitude, the strength of the signal is going to change. So I'm going to send a short pulse for a 0 and maybe a long pulse for a 1. And maybe I could change that up if I felt different in the end. Whoever designs the system gets to decide how it works. But generally, it'll be some kind of pulse. For frequency shift keying, we're going to change the frequency a little bit. So we might have a slightly lower frequency for a 0, slightly higher frequency for a 1. Everything we're looking at today is amplitude shift keying, so nothing super complicated. This is it. This is our first mystery signal. This is our encounter. We've wandered around trying to figure out what this is, which this is basically me walking around my apartment let's find some signals. What does this do? And so this is something that I just found. Does anyone want to guess what it is? I know it's super hard to tell. You only have yeah, it's a remote. Someone said remote, yeah. You caught me. It's not very complicated. So this is just like a light switch. Yeah, I got it on Amazon. It came from China. Sounds like a great recipe for security. It's very affordable for me as a user. I want a cheap device, which is great recipe for security. And I've got buttons where I can turn switches on or off. This came with, I think, 4 different plugs that you put into the wall, and then you plug your device into it, and it'll receive this signal and turn on and off when you push the buttons. So this is cool. I don't have to get up and turn my lights on and off, and that's great because I'm lazy. But, you know, I'm picking this up and I'm looking at it and I'm realizing just looking at it, we're not understanding the signals that it makes. We don't know how it works. We've just got a plastic cheap box that turns things on and off. So how are we going to learn about this? It's like if only we had something like a tool, like a signal dex, and you just, you go out adventuring, you've got your backpack and you've got your running shoes and the smell of fresh adventure is on the air, and you pull out this little encyclopedia, point it at a signal, and it says, I got you, I know exactly what that is, how it works, what it does. It would be really cool if that existed. Maybe somewhere. So I did a little bit of research. I was like, there's no way there's something that could make it that easy for me. There was. Really excited about this. So RTL 433 is one of the tools that we'll be looking at. It's a command line tool. You run it, and it will look around a given frequency and decode the ones and zeros for you. So you don't need to sit there tuning around and trying to be like, did it go up? Did it go down? Like, what's the pulse length here? It'll chop that all up for you and show it to you. It'll also do device discovery, which we'll look at in a little bit. But here we've got the RTL 433 with the dash Q and the dash A. The dash Q is just to make things quiet, and the A, it's kind of like operating in discovery mode, looking around for things. And you can see we've got here a signal that we don't care about. This one is not relevant to the testing, but maybe it's just something in the neighborhood talking as devices do. And then we've got down here, I start pushing the button on the controller, and you can see the same signal over and over and over, sort of calling out to that switch, turning the light on again and again and again. Or if you hold it for a longer time, it'll make the same pulse. So in video, that ends up looking something like this. So here we've just run that same command, and you can see as I push the button, we get the signal back. We start seeing, maybe there's like a smart meter or something nearby that's got a similar frequency. But, we can push the buttons. As I push different buttons, if you're paying close attention, you'll notice that some of the ones and zeros are going to change. So those are for different buttons. But if I come back to that same button, it looks exactly the same. Surely that wouldn't mean something, would it? Like a security thing or let's just forget about that. It probably doesn't matter, right? Probably doesn't matter. So this is the part where it's kind of like a baking show. I'm like, well, here, look. Here's the signal, and we can reverse it by lining up all the bits and bytes and sort of theorizing how it works. And I can just be like, ding, I already have a tray of cookies done over here. So this is the done tray of cookies. This is me pushing all those buttons and seeing what does the on for switch 1 look like? What does the off for switch 2 look like? And if we chop it up, so I've added some spaces to kind of see where it looks like things are similar. So you see the first 10 bits or so are all the same. So let's assume, just go out on a limb, say that's the device ID. It's saying which remote it is. So maybe my neighbor has the same cheap remote. We don't want to turn our lights on and off at the same time. That would be kind of silly. So this is like the introduction of saying, hey, this is who I am as a remote. After that, it seems to be consistent where that 01 shows up for which switch it is, and 11 if it's all on or off. So maybe it's some kind of like selector, like, hey, turn on just one or everything. And after that, we've got some level of which switch it is. So you'll notice the switch number is consistent, and then we've got the on and the off look consistent. So we can like translate these at this point. I could receive a signal, someone could push the button for me, and I could just receive it in this way, using RTL 433, and be able to translate, oh, this is the switch saying its name. It's saying to turn on switch 2, and that's what's going to happen. So as simple as it looks, hopefully by this point, this is the reversing, right? This is like very basic signal reversing. We're pushing a bunch of buttons and figuring out how it works, which is cool. Like this is our first, we've caught a signal and we've understood that signal. So that was backwards, there we go. So now we've got another mystery signal, right? We want to keep challenging ourselves and learning more things and adventuring around. Does anyone want to guess what this is? I know it's really hard to tell.
Remote control.
Whoa, a remote control. That's a great guess. What kind of remote control? Fan, yes. We have very smart people in the audience because it's very hard to tell what this is, isn't it? So this is a fan remote that was in my apartment. more me being lazy. Of course, I don't want to like turn a fan on and off with my hands all the time with a switch on it. That would be annoying. And it's got some light controls too. This one looks a little more complicated than the last one, which is cool. Maybe we've got an opportunity to use new tools. So for this one, I tried running RTL 433 because why not? You know, with the same exact options as before. What's going to happen there? It didn't work. So this means one of two things. One is that I'm doing it wrong, which is always a possibility, right? I am human, I think. The second is that maybe it's at a different frequency. So RTL 433 has got an option to tune it to a different frequency to look at, but it's not going to find that on its own every time. It's only going to look at like a little bit of slice. We have to know around where that signal is. So maybe this is a chance to look at something new. We could tune around with GQRX, but maybe we want to make our own tuner, right? Maybe this has been really just so much fun for us that we wish we could just take all the pieces of a radio and slap one together ourselves and make it ourselves, almost like Legos. And there's a tool for that too. So the GNU Radio Companion is a great way of putting together the little bits and pieces that translate software signals and then getting the display or the output that you want from them. So to kind of put that in perspective, GQRX is a tool that uses the GNU Radio libraries, but the Radio Companion builds tools that use that. So it's kind of like either a step up or down, depending on how you think of it. You get to build your own things, but you're still not, you know, left out to code everything by hand. It's very visual. It looks something like this. So this is the block diagram that we get. We've got like our little toolbox over here, which is all the different ways of translating signals and things we can do with signals, the outputs that we can take, the ways we want to display it. In the middle, we have the RTL SDR source, which is the most important. This translates for us. So this does all the heavy lifting of taking those little bits of signals and then turning them into ones and zeros for us. And we can then feed that into some different displays. For this one, I chose the fast Fourier transform sync. So it does a bunch of math that makes it possible to see the amplitude at nearby frequencies. So kind of like with GQRX, how we could see what was going on around us in the spectrum, we get to do that here too. And then I also want something that shows me the change in amplitude over time. So maybe if we've got that amplitude shift keying, we've got a pulse, we want to see that happening. We want to see like, what does short look like? What does long look like? So that'll give us that view. We've also got the GUI slider way over on the left here, and this is the thing that we can grab to tune with. So if I was just making this and putting in 300 megahertz, and I'll have to step away for a second, here, then it would just be stuck at 300 megahertz. I wouldn't be able to tune it. We need something that we can use to explore. And in this case, it'll be this sort of variable, the GUI slider. In this case, we'll just call it FREQ. So it's like a variable if anyone's done coding. And then you just reference that variable in the RTL SDR source so it knows what frequency to tune to. When we grab that button, drag it back and forth, which you'll see in a second. It'll make a little bit more sense then. So we've got all these together. We've got our bits and pieces, and we're just going to press that play button, and it'll make us a radio. Just like this. So this is when you press play. You can see we've got the fast Fourier transform, and then we've got over time the amplitude for whatever our set frequency is. It starts out really, really like zoomed in on a specific set of time. So right now we're at microseconds, which we don't really need. We want like seconds, right? So we're gonna step out a little bit, maybe look at over milliseconds instead. That seems a little more reasonable. And now we can take that button up in the top left and drag it back and forth between where we think the signal might be to see what's going on. And then, you know, in the background, you can't see the part where I'm just like mashing a button like crazy, seeing what's gonna happen. So we start pulling it along in the range of frequencies where maybe it is. We see a little bit of jumping, but nothing really coming out yet until this, right? So it just pops up. It's like, there it is, bam, this is our signal. We found it. You know, if I stop pushing the button, it'll stop showing, and if I mash that button again, it pops up. But we can't really tell what's going on here, right? This is pretty dramatic, so maybe we want to zoom out again. The fast Fourier transform plot comes in really useful here because you can see the peak. If you turn on the peak hold, it'll show you peak amplitudes, and it'll kind of hold on to that. So even if the signal is jumping, you can get a sense of around what frequency that happened at. And then as we zoom out, we can start to see these pulses coming in when we hit the button. And if you'll notice, some of them look a little bit longer and some of them look a little bit shorter. Go figure. So we've made it to the ones and the zeros. We can see them with our eyes. This is in the air, right? I mean, like metaphorically, you can fight me on the science of that, but it's pretty cool. It's around us, and we've got ones and we've got zeros, and we're looking at them on our computer for $30, which is pretty cool. But at the same time, as excited as I am, as thrilled as I am in this moment, I don't want to take out a notepad and start writing down like 1, 0, 1, 0 for every button that this controller has. But now we know where the signal lives. We know it's at around, for anyone who can't read up in the corner, it's at like 304.1 megahertz, we'll call it. So for anyone who remembers with RTL 433, our favorite friend right now, we can just tell it where to go. So just sort of a recap on that video portion. And then we can make it do the heavy lifting for us all over again. So we can just give it a -F flag for the frequency, give it around 304 megahertz, let it do its thing, and it will pick up those ones and zeros that we were seeing back over here. Exact same stuff. Great, much easier translation, right? So now I can go and reverse this one without having to do quite as much work. This was a slightly more complicated controller, so if you have or have seen anything like that, it would be a really fun exercise to go try, replicate that and see, you know, how do the buttons work, how does the fan speed work. It's cool stuff. So awesome. Now we've caught 2 signals and we've understood them, which I think is the really powerful, awesome part. So why don't we just keep going? Let's do another. Let's do like one more. This is our 3rd mystery signal, and I know you can't tell what it is. It's so mysterious. The shape is not determined at all. It's very strange. Does anyone know what this signal is? Can anyone help me? It's a car key. It is also a remote control. Thank you, Tacitus, but it is a car key. We have people who are very clever all across the audience. So this is a car key and a mystery signal. How does that work? Let's so for this one, I'm going to kind of assume that maybe it's in the 315 megahertz band. I've heard that the signals of type car key like to live in the 315 megahertz band. So let's try pointing RTL 433 there. So we do that, and what do you know? We start pressing the unlock. We're like, man, maybe this will be just like the light switch, right? Which, rewinding a little bit, does anyone remember with that light switch, I push the button and it looks the same every time. Can anyone guess why that might be a problem? Nervous laughter. Does anyone want to vocalize their fears about this control? Thank you, yes, so replay attacks with my light switch. So if I'm using that light switch and my friends are in the neighborhood, which there are many of my friends in the audience who may come by and decide to visit and mess with my lights, not a great light switch for that. So anybody who could transmit could play the exact same thing. They could catch the signal of me turning on the light and then play it again whenever they want and wake me up at 3 a.m. If I'm not already, you know, staying up late doing radio things. Maybe they could turn it off. That would be no fun. But anyways, so for this one, we're thinking like a car key, right? Maybe this will be the same. Maybe it'll have a replay attack. That would be really cool, wouldn't it? We'd get on it. It'd be so cool. Security's broken, right? But we start looking at this, and we notice there's some consistencies in the beginning of the signal. For this one, we've got the same. It doesn't show up perfectly, but we've got the 03, 88, 40, and that looks the same for the hex representation of the bits. But after that, it changes every time. And that's no fair, because then we can't replay attack on a car. Hey. So, you know, with things like that, we've got a little bit more security going. Maybe we can't expect high-grade encryption like how our computers are communicating on a regular basis, and maybe if you're holding onto a car key for 10 years, you can't necessarily expect someone to show up and like factory upgrade the encryption of the controller. Maybe one day. That would be kind of cool, actually. But we still can't do a replay attack. We can't get away with it this time. We've been foiled. So in this case, I did do a little bit of research on that specific controller, and somebody had done a survey of the insecurity and security of different car controllers, car fobs. So for me, that would be like my next steps, right? I've gone from the beginning town to looking at a car key and kind of understanding what's going on, which is a pretty cool, stepping things along and advancing my knowledge. And maybe it is still insecure. So another fun trick that you can do with RTL 433, you can just discover. So here you'll notice I've taken away the -Q and the -A flags, which means it's gonna, for taking away I think it's the -A, it will load all these profiles of devices it knows. So for all those things in the neighborhood that you were just seeing the raw signals for before, now if it recognizes something, it'll tell you. So I'm just listening to signals in the neighborhood, as one does one day. And down here we've got a Toyota TPMS is what it's called. And it's a tire pressure monitor system. So for anyone who's not familiar with this, tires will report their status of their pressure in some way. But every tire has a unique address, kind of like a MAC address thing going on. And if you had a unique set of tires that were attached to a unique car and a unique person owned that car, and you could tell where their tires were at certain times of the day, you might know where that person is at that time of day. So TPMS stuff has actually been used for tracking a little bit in the past. So we've got that more surprises that you find along the way type stuff. And that's just investigating whatever's around. So at this point, we've gone from what is a signal all the way through I'm decoding a car key, which I hope is a pretty satisfying experience for all of you. It was for me. I loved that adventure. If you want to continue that adventure, I've got some resources coming up. But sort of as a closing reflection, yeah, that light switch controller is not secure at all. And if you think about how many different RF controllers are out there in the world, you've got industrial cranes and you've got all kinds of different systems that talk to each other with RF, and they might not have quite as strong motivations for security, right? You think about the computing power you're going to have in a remote control that's not for a light switch, that's for something a lot more important. It's going to have a similar level of power, and its security might not be there. So even though we've just been looking at how to mess with my life today, there is definitely applications you can get in surprising places by looking at this all around the world around you. Things are getting better over time, as with a lot of security things. We definitely, there's something satisfying about stomping your feet and saying everything's broken, but they do get better. They really do, little by little over time. So, and the more people we get looking at these things and getting curious about this stuff and just kind of saying, I found this, and should it really be that way? Someone might not have looked at it before and said, hey, is this okay? Is this expectable? Is this secure? So being able to take that security mindset and apply it to something new, not only are you potentially going to help out an area that doesn't have as much support in security, but you're also going to be able to just sort of sharpen that security mindset, right? Look at something new, something you've never looked at before, learn new tools, push yourself out of the comfort zone little by little, and make it to much more greater challenges, right? So I don't know if there's an Elite Four of signals. That would be pretty cool to line up, but you get bigger and badder challenges. And with more curiosity, eventually, you get more solutions by keeping that open mind, thinking about how could we improve this? What is the next step? So if any of this piqued your interest, if you want to keep investigating this stuff, then there's a lot of great ways to do that. For anyone who is interested in amateur radio, I know we had exams last night, so you could try and find someone and ask them about it. There's also the ARRL, so they're an association that does a lot of amateur radio stuff. Very welcoming community who always loves sharing what they know. And then if maybe the OSINT part of FCC IDs intrigues you, so every time someone registers an FCC ID, they have to submit papers on what's going on, right? And some companies that are a little less experienced with this, they'll say, oh, yeah, you can know all about my device. Here's the test report, and here's the circuit design, and here's that one note we sent to the manufacturer that one time. They'll just and that will get listed publicly. So you can learn a lot about some of these devices. If there's a bigger company, like Google, Apple, they're probably not gonna submit that. They know, they're used to this, right? They've got a sense of what they're doing. But sometimes you can find some pretty fun stuff there. And you can also see new devices that are coming out. You can see new registrations and kind of squint and say, is that really, do we need that? But why did someone make that? So it's fun. If you're really curious about just playing with software-defined radios in general, I cannot recommend more Michael Osman's materials on this. So he has a series on using the Hack RF on the Great Scott Gadgets site, but you can really use it with any radio you want to. It's amazing material, and he does a really great job breaking it down and explaining it and making it easy to follow. And if the research side of it is fascinating to you, if you want to think a little bit more of the car stuff, or some really fun tricks that you can play in the world around you, Sammy Camcar's got some great stuff on both the security of cars and RF stuff, and wireless doorbells, right? There's another thing where maybe somebody wants a wireless system, but it might not be super secure. And also the paper that I mentioned on looking at the security of car fobs in general. There was a great Usenix paper on that. So that's all I've got. And does anyone have any questions? Also, slides are up at that URL, just to mention that. So if you want to go back and look at any of this, then, or your phone pictures aren't good, then definitely check that out. Yes? Could you say again? Sorry.
When they're registering a device in the FCC, they don't have to, do they have to, or I'm asking, do they need to state what frequency the device is going to use?
So, thank you. The question was, when you're registering a device with the FCC, do you have to state what frequency is used? Definitely. So the FCC manages basically all the different frequencies for the US, and they're going to tell you what power you're allowed to use at different frequencies and how to play nice with other devices. So when you do those registrations, it's saying, hey, I'm going to make a device and it's going to do this at that frequency, and basically here's how I've done my homework to make sure it doesn't mess up somebody's day or interfere with something important, or transmit really with too much power and do something dangerous. Does that answer the question?
Yes.
I'm saying yes. So when you register with the FCC, you need to tell them what frequency you're operating at for that device. Yes, sorry about that. Any other questions? Yes.
Have you thought about transmitting as well to interoperable systems, or?
So the question is, have I thought about transmitting? I've definitely thought about transmitting. You can do a lot of really awesome things with that. The reason that for this talk there's no transmitting is it's a lot easier to talk about the adventure when you don't have to also talk about the FCC regulations involved with transmitting. So to give a little more context on that, if you're testing different systems and transmitting to different systems, you are also subjected to those FCC regulations. So you need to think about very carefully about what you're doing with what systems. The other thing is there might be unexpected behavior if it's not your system, if it's somebody else's RF device. If anybody wants to play around with the transmitting side without worrying as much, then definitely make sure you've got a Faraday cage, so some metal to block the signals. You get your own sort of, this is my world of RF, and whatever I transmit won't get out of this box. So you at least know you won't cause any trouble. You'll just do damage to yourself if something happens. Any other questions? Yes.
So I was a little bit late, so I don't know if you covered this or not. One of the questions I had, it kind of dovetails with the transmission question, but talking about the noise floor capabilities of these devices and how susceptible they are to not necessarily jamming, but just passive interference. I mean, I don't know if there's anything.
So is there a specific question you want to ask based off of that?
Well, I guess the question I have, so you talk about the variance you have over in the time domain of the let's say your key fob. So one of the things I've seen in the past is these key fobs will stop working in high noise environments, high RF noise. Is the RTL SDR capable, without simulating that in the high noise environment? So without actually, by going to a high noise environment, will it be able to tell you what the other capabilities of the receiver are?
Okay, so I guess I'm going to answer the question that I'm hearing, and then if I got it wrong, you can ask another question. if that works out. So the question that I'm going to answer is, can the RTL SDR handle interference, if something gets jammed? Can it characterize the interference?
So if, let's say you've got, so you walk up to your car and you put the button on, it happens. You take it, you go, what's going on? Is the battery dead? Or you pull out your laptop, you look at the frequencies. Are you capable of determining what the noise environment is so that you can set thresholds for what the capabilities or jam resistance of the device are?
Okay, so I guess to the general situation of the noise floor, and then if you want to keep talking about this after, then I'm definitely interested in that. But just to provide some general context on the noise floor, when you're working with RF signals, things in the world around you also make RF noises, and they might interfere with what you're trying to do. So if you've got a car key, and maybe there's somebody else who's transmitting very rudely on the same frequency as that car key, so your car can't hear the key unlocking frequency, or well, it's hearing all that noise, right? So somebody's going to transmit it's like the equivalent of shouting, right? If somebody's shouting, then I'm not gonna hear your question if someone just stands up in the corner of the room and yells. So it's like the RF equivalent of that. There are a lot of ways with advanced processing of signals to cut that noise out as much as possible. But if it is loud and interfering a lot, then you're kind of out of luck. Yeah. There's also ways to work around it. So if you have like what's called a noisy environment, you can do things like a more complex system might change frequencies every once in a while. So maybe the system has a way of saying, hey, I can't really hear you over here. Can we step 5 kilohertz over this way and try again? So I think that is a little bit about the noise floor stuff. And then absolutely, if you want to talk about that more, or if anyone else is curious, then let me know after this. Yeah. Then I'll look forward to chatting about that. Any other questions? Awesome. Well, thank you so much for joining me for this. I love sharing this talk, so I appreciate you all being here.